All right, so in this lesson we're going to start looking at ways that magnetic fields get created. So in the previous chapter we really looked at how magnetic fields influence moving charged particles and how a moving charged particle moving through a magnetic field experiences a force. But the odd thing about magnetic fields is that a moving charged particle creates a magnetic field on its own. What that force really is the interaction between the two magnetic fields. A magnetic field created by the moving charged particle and a magnetic field that actually exists from whatever source you had from before. So in some substances, the motion of electrons within them gives them magnetic properties. And in fact, if you look at ferromagnetic substances, paramagnetic substances, and diamagnetic substances, what you see is that the way the electrons are moving, or the arrangement of electrons in the substance itself, in that matter, gives it the properties that it has magnetically. Now, we won't cover this in class. I've occasionally, when I taught chemistry or AP chemistry, covered these ideas in chemistry, how you can determine or how you can predict whether or not a pure element is going to be diamagnetic, paramagnetic, or ferromagnetic. There are some ways to do that. But if you're interested, look it up. It's pretty cool. It also works out that electric current can create magnetic fields. And so some places that we use this in our everyday world, if you make an electromagnet, you're basically creating a magnet using an electric current. If you use a solenoid, basically an electric current that's wrapped around many times a coil. Think of like a slinky that you put an electric current through. That will create a magnetic field. Any type of wire coil creates magnetic fields if you put a current through it. Now, what I want to talk about next is what I call the permeability of free space. And so the permeability of free space is a similar type of concept to the permittivity of free space. Remember, we were talking about electric fields. We had this value epsilon 0, which had this really small value. And this really talks about how the electric field travels through free space. Now, it's worth pointing out for magnetic fields, we have a very similar constant. How do magnetic fields travel through the vacuum of space? And the value of mu 0 happens to be 4 pi times 10 to the negative 7th. That seems like a really odd number to me, and it's crazy that it's 4 pi, but it is. So this may seem a little strange, but 4 pi is the exact value, to the best of our knowledge, of the permeability of free space. Now, there is another weird relationship here between the permittivity of free space and the permeability of free space. And the other weird relationship is if you square the speed of light, you get the value 1 over epsilon naught times mu naught. That is really strange to me. So this actually says there's a little bit more going on when we see electric fields and magnetic fields, and the fact that it relates to the speed of light really is kind of odd. And we'll get into that later on when we start talking about Maxwell's equations and what Maxwell's equations really do for us. It's a way of bridging electric fields and magnetic fields and showing that they are very closely related to one another. So let's look at a single moving charge. And so we have this moving charge moving through space and want to figure out the magnetic field at point P away from the charge. So I would have something that looks actually pretty similar to my electric field equation. That magnetic field is related to Q and V. So Q times V divided by R squared. That mu 0 over 4 pi is really our constant that we have that gets pulled out. And then sine of whatever that angle is. The direction of that field can be given by the right-hand rule. If you put your thumb of your right hand in the direction that a positively charged particle is moving, your fingers curl in the direction that the magnetic field is produced. So if you have something moving to the right in this case, the magnetic field looks like it goes out on top of it, down in front of it, in on the bottom of it, and behind it looks like it's going to go up. So this would be the way I would calculate the magnetic field from a single charged particle with a charge Q. And so this value phi is going to be whatever this angle is right here between the direction of travel and the radius. It's worth pointing out that this is also a cross product, that you can find that direction using the cross product. Now, what if we were, instead of dealing with a single charged particle, what if we're dealing with a wire that has current in it? So looking at the magnetic field created by many moving charged particles. If we have a wire, we put current through it, really that's what's happening. So we're going to look at a small piece of current rather than individual charges within the wire. So think of this as I'm looking at chunk dl of the wire, and I'm trying to find magnetic field caused by that chunk. What happens is, if we think of what q times speed would really be, remember I is really q divided by time, so really dl divided by time is speed, so we do have the exact same equation here. And so the magnetic field caused by this little part of wire is equal to mu naught divided by 4 pi I times dl cross r. What r really is here, or r hat, is a unit vector in the direction of r, and then divided by r squared. So really what this cross product does is it gives us that angle sine of phi in there. Remember that r hat, a unit vector, is a magnitude of 1 and just points in a direction. So if we look at a long straight wire, if we actually try to do the math here, we'd find is that this is a long wire or a long line of moving charges, we'd have to integrate this thing. Unfortunately, this is not necessarily the most fun integral to do in most circumstances, and as you probably guessed, kind of like integrating electric fields, this only really works with very specific types of situations. Now, if you actually solve the integral equation for a long straight wire, say a wire that is infinitely long compared to where you're at, what you find is that the magnetic field is equal to mu naught times I divided by 2 pi r. And so you end up with an equation that looks like that for the magnetic field caused by a long straight wire. So if you did this integral and actually figured out how does a magnetic field vary based on L and R, or really this distance and this distance, x and r, and we made one of those x much bigger than r, you'd end up with this expression when you actually work it out, where r is the distance you are away from the wire. So if you actually solve that out, you get an equation which is pretty easy to work out and not too bad to play around with. Now let's take a look at a situation where we have two long straight wires that are perpendicular to the plane of the page. One carries a current out of the page, that one would be the one on the right, and one carries a current into the page, and that'd be the one on the left. And let's say we're going to try to find the magnetic fields at point P1, P2, and P3. Each one I've said is a distance d away from the center point, which is P2. P3 is located d to the right of the right wire, and P1 is located 2d to the left of the left wire. So if we actually work out what's happening with the left-hand wire, I think I'm doing P1. If we look at that, the magnetic field caused by the wire on the left should go up. The magnetic field caused by the wire on the right should go down. And so I should have something that looks like magnetic field of one wire minus magnetic field of the other wire. Remember, magnetic field is a vector, so we're going to add these like vectors. So magnetic field of wire 1, which is the one on the left, will be mu naught I 2 pi 2d minus mu naught I 2 pi 4d, the wire on the right. If you add those together, you get the magnetic field to be mu naught I divided by 8 pi d, and it's going to be pointing up at that location. Now if we do point P2, what's true about the magnetic field from the wire on the left is it points down by the right-hand rule. The magnetic field on the right from the wire on the right also points down by the right-hand rule. So these two magnetic fields would add together. In this case, for each one of the wires, it's going to be mu naught I divided by 2 pi d, so you end up with mu naught I divided by pi d downward. So you'd have a stronger magnetic field at the location between the wires than you do at P1. which I don't think is all that shocking because you're closer to both wires in this case than you are at P1. If we do P3, what happens from the wire on the right? You have a magnetic field that points upward. From the wire on the left, you have a magnetic field that points downward. If we plug in the values for distance, we end up with mu naught I divided by 3 pi d upward as your total magnetic field. And so that gives you a quick overview of how we can calculate the magnetic field from a long straight wire. We could also look at magnetic fields from, say, a coil of wires. And we'll probably do this in class, if I had a coil of wires and I was looking at the axis that goes right through the center of that coil, what is the magnetic field along that axis? That happens to be another situation that's easy to calculate. Kind of like I said with doing electric fields by integration, in using Biot Savart law really requires that you have very specific types of geometries and arrangements in order to even get an integral that's possible to solve. So that kind of does a quick overview of Biot Savart law. We're going to look at what happens if you have these two wires like I had here. What happens to the interaction between them? If you have current in one wire that's creating a magnetic field, well, that magnetic field can interact with the current in the other wire to cause a force on that other wire. And we're going to look at how we deal with those types of situations in the next lesson.